algebra for computer vision. I'm going to take Joe out to dinner at 6:45 at Evelyn restaurant in Warwick. If you'd like to join us, please let me know immediately after the talk. I'll be standing here taking names. I'm reminding you, thank you so much for coming, but there's strictly no texting or using of any electronic devices during the talk. Thank you, including John. Thank you.
Thanks everyone for coming. I'd like to thank Doran and Nathan, the organizers, for the opportunity to speak here. I'll be a postdoc in the area starting in August. Okay. So I want to give you the context for this talk and also my thesis. I say my thesis is about algebraic vision. So what is that? So multi-view geometry studies 3D scene reconstruction from two-dimensional images. It's a traditional area of computer vision. Applications to self-driving cars nowadays. It has foundations in projective geometry, building the 3D model from the 2D images. Algebraic vision bridges to slightly more sophisticated areas of algebraic geometry. So here are a few recent conferences in algebraic vision to prove to you that it exists. I'm actually organizing a summer school in Germany, also in algebraic vision, this July. So today I want to tell you about a numerical algebraic geometry project. That's the single-authored part of my PhD thesis. It's going to appear in the new SciAm Journal of Applied Algebra and Geometry. Okay, so first the background, more about 3D reconstruction. Okay, so here's an example from a highly cited paper called Building Rome in a Day by Samir Agarwal, first author, and others. He's now, by the way, a vision expert at Google. At the time he was at Washington. Okay, so the input in this paper was the top 2,000 Flickr search results for Colosseum. Nothing else. The output was a point cloud of about 1 million points, and then the orientation of the 2,000 cameras that took the images. So you can see these little triangular prisms, they represent where the camera was positioned and how it was pointing. This point cloud constitutes the 3D model of the Colosseum. So any questions about the input and output? This is how this works. Okay, so how does Google do this? So roughly speaking, their pipeline has 3 steps. They first identify pairs of images that overlap in their view. And then they do reconstruction on those pairs. So they determine the position of the cameras that took those 2 images, and then some points in common in the 2 images. Finally, they piece together these local reconstructions.
Might I have a question?
Yeah.
So you're being handed different images from cameras taken at different angles, or
Yeah.
Okay.
Of the same scene, but just they might not even overlap. They might be totally different
But
angles.
you know the angles going in, right?
No, you don't. You pulled this from Flickr. You just have 2,000 search results. You know nothing. You just see the images.
Oh.
Okay. You really just see the images.
Okay.
Okay. So yeah, the first step is which images overlap, and then do local reconstructions and piece together. So, okay, so which of these steps do you guys think is most algebraic?
The last one.
Okay, actually the middle one is what I'm going to be talking about. So I'm going to be talking about small reconstructions. So for people in computational algebra, tiny reconstructions are subroutines in large-scale reconstructions. And the tiny ones rely on super fast, specialized polynomial equation solvers. So the key point here is that we can actually formulate reconstructions with polynomials. So here's a highly cited work where they studied several of these polynomial solvers, and this paradigm for doing reconstruction appeared in 1981. It's called random sample consensus. Okay. So let me tell you what a camera is here. It's simply a full-rank 3x4 real matrix up to scale. So why does that model a camera? Because a matrix gives a map from 4 space to 3 space, but I can think projectively. Say that's a linear map from P3 to the projective plane. X goes to AX. This is all a camera is in this subject.
One quick question.
Yeah.
Is there any reason why you want to think projectively when the scene itself presumably is localized in some compact region?
So thinking projectively gives you a richer family of cameras. Okay, it's on the affine patches. It's actually not just linear projection. Okay.
Oh.
Okay.
The full projective.
Yeah, but on the projective space, it's a linear projection, but on affine space, it's not. So you actually want to be able to model things where you divide as well in affine space, and you can cleanly do that by lifting to projective space. Okay, so this is sort of classical. This is the setup in multi-view geometry. It's been very fruitful in vision. Right, and so the little dictionary is that P3 represents the world, so P2 is the image plane. Now this full-rank 3x4 matrix has a unique right kernel up to scale. It's a point in P3. And that represents the camera center. So a camera can take a picture of any point except its center. These last two features are take a little bit more explanation, but they're really crucial for what we'll discuss. So, given a 3x4 real matrix A, we can factor it as a 3x3 upper triangular matrix. Let's say something like this. Times a rotation, a 3x3 rotation, and another concatenated with a column. So any 3x4 matrix, provided that the left 3x3 submatrix is non-singular, can be factored in this way. It's due to it's called the RQ factorization of the 3x3 left submatrix at A. Okay, upper triangular times rotation. So this bit here has an interpretation in vision, this upper triangular part, and we say it stores the internal parameters of A. So, for example, the focal lengths on the diagonal. These coordinates are the principal point and skew. This part stores the external parameters of the camera. So in particular, the kernel of A is equal to the kernel of RT. So where the camera center is in 3 spaces an external parameter. And also the orientation of the camera, R, how the camera is pointing. Okay? So in the case when k is known, when the internal parameters are known, we can left multiply by the inverse of k and assume that this is the identity. In that case, the camera is called calibrated. Okay, so a rotation concatenated with a translation is a calibrated camera, RT. And that's a camera with known or normalized internal parameters. Okay. So this comes up a lot in practice. For example, if the camera is yours. If you know the camera, you know its focal length and its other internal parameters. The only thing you don't know is its position in the world. Then your camera is calibrated. Okay, any questions about this? We're going to be discussing calibrated cameras. Okay, what is a camera configuration? So notice that images alone do not determine absolute position of cameras. They only determine relative position. So from this picture, I can't determine if it's the actual Eiffel Tower in Paris, or if it's maybe it's the fake Eiffel Tower in Las Vegas, or maybe it's a miniature model of an Eiffel Tower. I don't know. However, if I had another image of this object, I could hope to determine the relative position of the two cameras. I won't know the absolute position in the world, but I could hope to determine the relative position of cameras that take the same pictures of the same object. Okay, so relative position is a configuration. So a configuration of cameras is just a tuple of cameras up to changes of world coordinates that preserve calibration.
What's Grassmannian?
This is related to the Grassmannian, yes, but precisely it's just a tuple of cameras where I identify two cameras if they're equal when I right multiply by a 4x4 matrix representing a change of world coordinates. And if I want to preserve calibration, then that matrix should, that 4x4 matrix should just be a scaled isometry. So a rotation, a central dilation, or a translation. So it should look like be a different rotation, let's say Q, something here. This something like this. Where Q is an SO3. And so these matrices form a group, and they act on P3 by translations, rotations, and central dilations. So we're going to try to recover camera positions up to this group action. Let me give you a warm-up. So how do I think about the configuration of two calibrated cameras? So two calibrated cameras up to rotation. I can globally rotate. I can translate or scale. Okay, so this is the classical construction. You start with two calibrated cameras. This means that the left 3x3 submatrices are rotations in both. And we think about the map from P3 to P2 times P2. So sending a world point to a picture under the first camera A and a picture under the second camera B. So the image in P2 times P2, these are all the pairs of points in first image and second image that come from a world point under A and B. It's a hypersurface in P2 times P2 determined by this bilinear equation. So we take A, stack it on top of B, and then put a column vector with the coordinates of the first P2 and a column vector with the coordinates of the second P2. The determinant of this 6 by 6 matrix actually defines the image in P2 times P2.
Like the hypersurface is given by setting the determinant to a particular value? And...
To 0.
Okay, it's the vanishing
of that. So the way to see this is, so the determinant equals 0 is equivalent to this matrix having a kernel. And let's think about what the kernel of this matrix would look like. Okay, it's a height 6 column vector. I claim the first 4 coordinates will give you a point in P3 that maps to x under A and x prime under B. So from the kernel of this matrix, you can get a pre-image. That's the main part of the proof.
Wait, and let's see how you're defining the map. You're defining the map by fixing the stars and diamonds and then picking things in the last 2 columns, the determinant vanishes?
The map is capital X goes to the pair AX BX.
Okay.
And a point is in the image, is in the Zariski closure of the image, if and only if this matrix has a kernel.
Okay.
So, okay, this is bilinear in x and x prime, so it can be rewritten uniquely as a x transpose times a 3 by 3 matrix times x prime. This is just a way to write down this equation. This blue matrix actually is how I think about the configuration of A and B. So the acting on A and B by a change of world coordinates, in fact, does not change the image in P2 times P2 of A and B. So actually just knowing which points correspond, which pairs of image points correspond, turns out to be equivalent to knowing the relative position of A and B. Just telling you this. So this equation, this given by this blue matrix, that's actually how I think about the orbit of A and B under the group. Okay? So this is a convenient choice of coordinates for calibrated cameras modulo the group action for 2 calibrated cameras. These blue matrices. So let me just ask you guys, what do you think the singular value decomposition of such a blue matrix is? So if you go through this construction for A and B, you get a blue. This equation, this bilinear equation, can be written in terms of the blue matrix. Okay, it turns out that this actually, what do you think the rank of this is? Just as a guess. Do you get any matrix this way? Sorry?
I would guess it's full rank.
Full rank. It turns out that it's actually, so a dimension count will tell you that it can't be full rank. So 1 calibrated camera is a rotation and a translation, 6 degrees of freedom each, but then we're modding out by a 7-dimensional group. So we should expect we just have a 5-dimensional set of such blue matrices. We won't get a general 3 by 3 matrix. Okay? Turns out that these are actually always ranked 2. And moreover, their top 2 singular values are equal. And actually that characterizes the matrices that arise this way. So that's a configuration of 2 cameras for me. A rank 2 matrix with top 2 singular values equal. This is from the multi-view geometry literature.
Can you do the same thing in n dimensions instead of 3 dimensions? The n-dimensional cameras in principle?
You can, in fact. So you can exactly look at the image in the product of the P2s, and that image will characterize the camera position, the camera configuration. But then you won't have a hypersurface. So you'll have a threefold in P2 to the n, and you won't get as concrete a description. You won't just say it's. And we're going to come back to that point. Okay, so warm-up continued. So what I want to do is I want to take this risky closure of the set of those matrices, blue matrices. I'll get a 5-dimensional variety by the dimension count I just did, and it turns out to be degree 10. Okay, so who here does not know what degree means for a projective variety? Okay, so what this means is take a linear space of complementary dimension inside projective space of 3 by 3 matrices. Okay, so that's going to be a 3-dimensional linear space. Intersect with E. You'll get 10 isolated points for a general choice of 3 space. So slicing E with a linear space of complementary dimension, provided that space is general, gives 10 isolated points. That's what degree 10 means. So it's sort of a measure of nonlinearity of the complexity of the. Okay, so in 2004, using a Grosvenor basis technique, a symbolic technique, David Nister built a solver that recovers 10 blue matrices, essential matrices, from 5 image point pairs. So an image point pair is just a point in the image of the variety from the last slide. So it's a point x and x prime in P2 times P2 in the first image and second image that are pictures of the same world point under A and B, some world point under A and B. And so if I give you 5 of those, then by the definition of the essential matrix E on the last slide, I know that E transpose times E prime must be 0. Okay, so E was, the definition of E is that it tells you which points correspond under A and B by this equation. So if I give you 5 points that I believe correspond, we have these equations. And we can and notice that they're linear in E. So each image point pair gives one linear constraint in E. Taking 5 image point pairs gives 10 possible essential matrices. So Nister actually worked out how to compute the intersection and get 10 essential point pairs. And he developed a super fast polynomial solver. And once he has E, he can recover A and B easily up to changes of world coordinates. So this was over 10 years ago, and let me just say his solver is used a lot in 3D reconstruction. So it was one of the key subroutines in the building Rome paper. Okay, so the effort for 3 calibrated views so far has proven elusive. How do you do this for 3 views? Don't have a good solver.
So far it's only for 2 calibrated views?
Yeah, so they really just do these local reconstruction on pairs. But people have thought about trying to do it on triples at once. Then you would have to do fewer local reconstructions. But there has been no solver has emerged. So this is what I want to
in
talk about.
principle, we could have built it, but it was too slow.
Sorry?
The same idea could have been used, but it was too inefficient.
I mean,
or it was not possible at all.
It wasn't possible at all, actually.
Not even
In the calibrated case, it was totally
so not even in
possible.
principle.
Yeah, there were no theoretical results. So I want to talk that I know. So in the rest of the talk, I'm going to talk about some theoretical results. Okay, so the title of the corresponding paper is Minimal Problems for the Calibrated Trifocal Variety. So it determines the algebraic degree. That's the analog of 10 for the blue matrices. For various parameterized polynomial systems, for the recovery of configurations of 3 calibrated counters. And the method is to take linear sections of a fixed variety whose points represent configurations of 3 counters. This is the analog of the blue matrices. And the computational technique is actually, it's not going to be symbolic, that's crucial. We're actually going to use numerics to solve these polynomial systems. So let me just explain this diagram, which is how we're going to solve these systems, find these degrees. Has anyone here heard of homotopy continuation?
I'm not going to comment on in general, but
Okay, so this is a little different in the topological sense. This is more like in terms of solving ODEs with Euler's method. Okay. So here's the idea. So you would like to solve the system f of z equals 0. Okay, so z is several variables. This is a polynomial system. And by solve, let me just say that I mean find the isolated solutions of, for example.
is f mapping it to, say, c or c to the n?
F, c to the n. So this is a system. Okay, so f is going to be like this. And it's an algebraic map. That makes the theory simpler. So, I mean, that's in general just a really hard problem, solving a system of polynomial equations. But the idea is, let's design a easy system with similar structure, with similar algebraic structure. So in particular, the equations should have the same degree in G.
So is one like a perturbation of the other?
Exactly. So I won't say precisely what I mean here, but okay. Well, let me just say. So I want the coefficients of the system F and the coefficients of the system G. I want to be able to view them as points in an irreducible variety, where the point corresponding to G is a general point. So similar structure. And then I form the homotopy, where I just deform from G to F. So T here is a real scalar, and I'm going to let it go from 1 to 0. So when t equals 1, the system is G. When t is 0, the system is what we started with, F. And in between, we're interpolating. And the main theorem is that, so for a generic choice of G, so